Welcome, everyone. Today, we are going to explore sets, subsets, and the complete logical definition of a subset. We will make these concepts easy to understand through systematic examples. Let's get started. What is a set? Let's start with an informal definition. A set is simply a well-defined collection of distinct objects. We call these objects elements or members. Let's look at a few intuitive examples. We can have a set of numbers, which we will call set A. Set A equals the collection containing the numbers 1, 2, 3, and 4. Or we can have a set of animals. Set B equals the collection containing a cat, a dog, and a fish. We can even have a set of colors. Set C equals the collection containing red, green, and blue. When working with sets, there are two key rules you need to remember. First, order does not matter. The set containing 1, 2, 3 is exactly the same as the set containing 3, 1, 2. Second, there is no repetition allowed. If you write a set as 1, 2, 2, 3, it is considered the exact same set as just 1, 2, 3. The duplicate 2 is simply ignored. Now let's talk about the belongs to relation, represented by this curved E symbol. On this slide, we will look at some true examples. Let's understand the notation first. When you see a little x followed by this symbol, followed by a capital A, it reads as x belongs to A, or x is an element of A. Let's set up our sets. Let set A equal the numbers 1, 2, 3, 4. And set B equal the animals, cat, dog, fish. Now, let's evaluate some statements. 2 belongs to A. This statement is true because the number 2 clearly appears in the list 1, 2, 3, 4. 4 belongs to A. This is also true because 4 appears in the list. Dog belongs to B. This statement is true because the dog is indeed inside the animal set. Fish belongs to B. This is true as well, because the fish is in the animal set. Next, let's look at the opposite, the does not belong to relation, which is the same symbol with a slash through it. Here, we will look at some false examples of belonging. The notation reads as x does not belong to A. Using the same sets, let set A equal 1, 2, 3, 4, and set B equal cat, dog, fish. Let's test some claims. 7 does not belong to A. This statement is true. Why? Because the number 7 is not in the set 1, 2, 3, 4. 0 does not belong to A. This is true, as 0 is absent from set A. 5 does not belong to A. This is true, because 5 is not listed in A. Bird does not belong to B. This is also true, because a bird is not in our animal set. Notice an important note at the bottom. The statement x does not belong to A is itself a statement that can be evaluated as true. It simply records a confirmed absence. Now, let's move on to the intuitive idea of a subset, denoted by this U-shaped symbol resting on a line. The informal definition of A as a subset of B means that every single element of set A is also found in set B. An easy way to think about it is A is entirely contained inside B. Look at the Venn diagram on the right. All dots of A sit inside B. Let's look at a true example with numbers. Let set A equal 2, 4, and let set B equal 1, 2, 3, 4, 5. Because both the number 2 and the number 4 are present inside B, the statement A is a subset of B is true. Now, let's look at a false example. Let set A equal 2, 7, and set B equal 1, 2, 3, 4, 5. The number 7 belongs to A, but 7 does not belong to B. Therefore, the statement A is a subset of B is false. We are now going to introduce a logical connective called implication, represented by a right-pointing arrow. We read the notation P arrow Q as if P, then Q.
Here, P is our hypothesis, or the condition, and Q is our conclusion, or the result. Let us go through the truth table for this implication in complete detail, row by row. In the first row, our hypothesis P is true, and our conclusion Q is also true. Therefore, the overall implication P implies Q is true. In the second row, our hypothesis P is true, but our conclusion Q is false. In this case, the overall implication P implies Q is false. In the third and final row, our hypothesis P is false, but our conclusion Q is true. Here, the overall implication P implies Q is evaluated as true. In the fourth and final row, our hypothesis P is false, and our conclusion Q is also false. In this scenario, the overall implication P implies Q is also true. Notice there is only one false row in the entire table. The implication is only false when the hypothesis is met, meaning P is true, but the conclusion is denied, meaning Q is false. That is the only betrayal of the if-then statement. To understand this perfectly, let's look at a real-life example in complete detail. Imagine a parent makes a promise to their child. If you score 90%, I will buy you a bike. Let's look at the first scenario. The child scored 90% and they got the bike. This is true implies true. The promise was kept, so the overall statement is true. In the second scenario, the child scored 90%, but they got no bike. This is true implies false. The condition was met, but the reward was denied. The promise is broken. This is the only time the statement is false. In the third scenario, the child did not score 90%, but they got the bike anyway. This is false implies true. The parent is just being generous. It's okay. The promise wasn't broken, so the statement evaluates as true. In the fourth scenario, the child did not score 90% and they got no bike. This is false implies false. This is fair, and there is no violation of the original rule. The statement evaluates as true. Finally, let's discuss the universal set and the concept of for all. The universal set is denoted by a capital U. It is simply the set of all objects under consideration for a particular problem. Nothing we ever discuss lives outside of this set U. For example, if we are only studying the numbers 1 through 10, then our universal set U equals the list of numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Everything lives inside this box. Next, we have the Universal Quantifier, which is represented by an upside-down capital A. When you see this symbol followed by a little x, it means for every object x in the universal set U. Think of it as a sweeping mechanism. We must check each and every element in the universe, one by one. If even one single element fails the check, then the entire for all statement becomes false. Looking at the diagram on the right, you can see our universal box containing numbers up to 10. Sets A and B are inside it. The universal quantifier will check every single number from 1 to 10 to verify whatever logical rule we give it.
Now let us bring all these pieces together to understand the formal logical definition of a subset. We write the statement A is a subset of B. By definition, this is equivalent to the following logical formula. For all x, if x belongs to A, then x belongs to B. Let us break this master formula down piece by piece. The upside-down A with the x means for every object x in the universe U. Next, x belongs to A is our hypothesis. It means if we find an element x that belongs to set A, the hypothesis is met. The arrow represents then it must follow that. And finally, x belongs to B is our conclusion. It means that element x also belongs to B, and so the conclusion is satisfied. But what happens when A is not a subset of B? Let's look at the negation of this definition.
A is not a subset of B if there exists some element X where X belongs to A but X does not belong to B. Such an element X is called a counterexample or a witness because its very existence witnesses the failure of the subset rule. Let us look at a formal verification for a completely true case. We have set A containing the numbers 2 and 4. Set B contains 1, 2, 3, 4, and 5. Our universal set U also contains 1, 2, 3, 4, and 5. We need to check every element X in our universe U to see if the statement, if X belongs to A, then X belongs to B, is always true. Let's slowly go through the table row by row for each element in the universe. For the first row, X equals 1, the number 1 does not belong to A, so the hypothesis is false. 1 does belong to B, so the conclusion is true. As we learned, a false hypothesis automatically makes the if-then implication true. For the second row, X equals 2, 2 belongs to A, so the hypothesis is true. 2 also belongs to B, so the conclusion is true. True implies true, so the implication is true. For the third row, X equals 3, 3 does not belong to A, making the hypothesis false. 3 belongs to B, making the conclusion true. A false hypothesis once again makes the overall statement auto-true. For the fourth row, X equals 4, 4 belongs to A, which is true. 4 belongs to B, which is also true. True implies true, resulting in true. Finally, for the fifth row, X equals 5, 5 does not belong to A, making the hypothesis false. 5 does belong to B, making the conclusion true. False implies true evaluates to true. Since all rows resulted in a true statement, the for all condition perfectly holds. Therefore, we can confidently conclude that the statement A is a subset of B is completely true. Now, let us examine a formal verification for a false case. Here, set A contains 2 and 7. Set B contains 1, 2, 3, 4, and 5. Our universal set U contains the numbers from 1 all the way up to 7. We must check if the statement X belongs to A, then X belongs to B is always true. Let's look at the key rows in our table. For X equals 1, the hypothesis is false and the conclusion is true, making the overall implication true. For X equals 2, the hypothesis is true and the conclusion is true, making the implication true. But let us skip down to the row where X equals 7. 7 belongs to A, so our hypothesis is true. However, 7 does not belong to B, so our conclusion is false. True implies false evaluates to false. We have found our witness. For all the other rows, the implication evaluates to true, but that simply does not matter. Because we found exactly one false row, the for all condition fails. Therefore, the statement A is a subset of B is false. The number 7 is the witness. It belongs to A, but is absent from B. A single counterexample is enough to completely break the subset claim. You might be wondering, why do we even need these formal definitions? Human intuition and vision are wonderful tools. Venn diagrams are fast and vivid. Our visual system can detect containment instantly just by looking at overlapping circles, and this works perfectly for small, concrete sets. However, human intuition breaks down in certain situations. It breaks down when sets are infinite, like the set of all even numbers, 2, 4, 6, 8, and so on forever. We simply cannot draw a Venn diagram for infinity. Intuition also breaks down when sets are highly abstract, such as sets containing complex functions, computer programs, or mathematical proofs. And finally, our mathematical reasoning must be mechanically verifiable, and it must be communicated without any room for misinterpretation. This is exactly what formal definitions let us do. They allow us to logically prove theorems where each and every mathematical step follows a strict, fixed rule. They allow us to communicate with zero ambiguity across all human languages. And most importantly, they allow us to program computers. A machine cannot literally see a Venn diagram. Instead, it systematically executes the logic. For all x, if x is in A, then x is in B, evaluating one single element at a time. This leads us to the central insight of this lesson. A computer checking if A is a subset of B simply runs a loop. It says, for each x in U, if x is in A and x is not in B, return false. This tiny block of code is the exact same thing as our formal logical definition. Logic and code are fundamentally the same thing. Let us wrap up with a summary of the concepts we have covered, along with our color legend. We discussed the sets A and B and the universal set U. We looked at the element or member X. We learned the belongs to and does not belong to relations. We explored the subset relation. We completely unpacked the logical implication, the if-then statement, and we used the universal quantifier, meaning for all. All of this culminates in the master formula. A is a subset of B if and only if, for all x, if x belongs to A, then x belongs to B. We can view this profound formula from three different perspectives. Through human intuition, we picture set A drawn completely inside set B using a Venn diagram. Through formal logic, we require that every single element X passes the logical if-then test. And through the lens of a computer, we simply write a program to loop over the entire universal set U, checking the if-then condition each and every time. I am so very grateful for your kind support. It truly means the world to me. Please consider liking, sharing, and subscribing to join our gentle community, and I would truly love to hear your wonderful thoughts in the comments below.